go back and watch the video again and read my book, right? But let's finish this and move on. Plane wave. So the two ways that we talk about, one is taking the curl. If you take a curl of one, you can get to the other, right? The tricky part on this is you need to you need to remember how to deal with the complex number J, and how does the sine theta plus or minus 90 degree works? Is that equal to cosine or minus cosine or whatnot? So you need to know that. And then the second way, which is the one that I highly recommend you to get good at, is the three rules. Because the curl always works based on the Maxwell equation. So there's no if, no but. The three rules works most of the time for the cases that we deal with, as long as you know the direction of K clearly. Right? It doesn't always come so clear. If you look at the first exercise in my book, the Maxwell equations problem, first problem, the direction of propagation is not clear. It's not clear because it's not a simple traveling wave, it's a standing wave. So when you look at the equation, you cannot pinpoint and say, hey, this is the direction of propagation. It's not as simple. So in that case, you have no choice but take the curl. It's a little bit more complicated, but you don't have a choice. For all other cases where you can pinpoint the propagation direction, these three rules always work, and I highly recommend you to use these three. Okay. So we'll do more examples when we are dealing with other topics or when we are adding more complexity to the problem. We will keep doing examples. But for simple examples, you need to go back and watch the video. Okay. The third method is even simpler. If you look at these two equations, right? So remember the three rules are, number one, E and H are in phase. So if I write this expression, if I know E is whatever cosine omega t minus kx, then this one will have the same phase automatically, because all you're doing is doing a cross product. You're not changing anything. You're not changing the function at all, right? So that's satisfied. And then the second rule is E hat cross HS is K hat, just the direction. E cross H is K, right-hand rule. But looking at this is the same, right? E, H, K, they're all in cyclic permutation. So this satisfies the right-hand rule, so is this one, E, H, K, right? So you can use this formula as well. And as far as the last rule out of the three, E naught over H naught is eta. So now if you look at this expression, this is hat. What is a hat? Unit vector. What does unit vector means? The magnitude is 1. So that doesn't contribute in your magnitude. So that means the magnitude of E over the magnitude of H is eta. And that's basically what it says. So one simple equation, it includes all the three rules right here. These two expressions are listed in your formula also, in your formula sheet. So sometimes this perhaps is the easiest way to solve the problem, but I don't really recommend you to rely too much on that, because you're losing the intuition of what's going on. In my past, the only time I see students use this expression is when the students were not prepared. They did not know what's going on. They saw the formula and just try to plug it in, and usually it didn't end well for most of the cases. So yes, if you know how to use it, it's useful, but I don't want you to rely heavily on it. Speaking of which, let me get thinking again. In the 30s problem, in the midterm, I keep telling you guys to forget about the motion EMF and just calculate this, and then take a time derivative. It works in every single case. Don't worry about the U cross B dot DL and then do. Most of you don't know how to evaluate this, first of all. You don't understand what this really means. So when you try to evaluate it, it did not end well. And also when this is not the full equation of the flux is this part is called the motional EMF. The other part is if you have a partial derivative dB dt dot dA. So if the B field change over time and the circuit also move in space, then you have to use both. Nobody really know this, right? Because I didn't talk about this. I didn't talk about it because we don't need to. Why make your life so complicated where you can deal with it with a simple recipe? I don't understand why people keep doing this in the midterm, right? It's like, I didn't cover this for a reason. You're digging a hole for yourself. But that's fine. It's your choice. So these two equations are there. I'm going to do one example. Like I say, I don't recommend you to do it. I don't want you to dig a hole for yourself again. But if for simple cases, if K is clear, this is like super useful. For example, this is one of the examples we did before. H is equal to this. I want to find E. So looking at this, automatically, I know what K hat is. What is K hat? Tell me. What's the direction of propagation? Guy. Negative C, right? So this is my K hat. I put this negative C here, cross this. That's super easy. So eta, this is in vacuum, so it's 377. H is just whatever is given. I just copy the whole thing here. Cross K, K is minus C hat. So X cross C hat is minus Y hat, but X cross minus C hat, that becomes positive Y hat, right? And then this is minus Y hat cross minus C hat. That means Y hat cross C hat. X, Y, Z. Y hat cross C hat is positive X hat. So positive X hat. And then this is your answer, right? So if you know what you're doing in some simple cases, these are very fast, faster than you use the 3 rules, faster than anything you can do, faster than the curl for sure, right? Okay. Any questions? So if you want to try to use this, learn how to use it, it's fine, but practice that. Don't just look at this example and say, hi, I know how to do it. Then when in the exam, I see a problem, I say, I don't know what to do. I'm just going to use this formula. Never end well, right? Ride your bike. Try a few times until you're comfortable, right? You won't just learn a song and then perform it the next day. Okay, so the next topic I'm going to skip, but you might read something sometimes called a Poynting vector. Poynting vector, you know the name. Okay. Poynting vector is nothing more than E equals H. This is called a Poynting vector, or S. What is Poynting vector? What is E equals H? Well, the direction of it. Remember, we say the second rule, E equals H hat, is K hat. So the direction of this Poynting vector is really my K hat, the direction of the signal propagation, where I'm sending the power to, where I'm sending the signal along the direction. The magnitude of it is called the power amplitude, because if power intensity, because if I multiply that with the area, I get the total power. So people use this a lot of time, like solar company, right? I want to know how much solar energy I'm getting. So I have to know the Poynting vector at that location, which including the directions and also the magnitude of your cell, like solar cell, for example, of the area receiving the power. Like I want to know how many cells do I need, right, for your house. If you use 10 kilowatt hours, how many solar panels do I need? The antenna, the dish, right? Yeah, the size of the dish too. Dipole, you don't really use Poynting vector because that's not an effective way to calculate the power. And we talk about the gain of the antenna, which including the directions and the power intensity. So what is power intensity mean? So we say the Poynting vector is equals h. So the magnitude is really, remember E naught over H naught is eta. So I can get rid of the H and write it as E over eta, or get rid of the E and write it eta times H. So this is the amplitude, the magnitude of the Poynting vector, the average give you 1/2, is E squared over eta or eta times H squared. So I want to point it out because electric field is related to voltage. And this is impedance. So this is sort of like 1/2 V squared over V, or V squared over Z, right? What is V squared over Z? The power, V squared over R, right? Power. What is H is related to the current. So this is related to 1/2 I squared times Z. What is I squared times Z? Power, right? V is IR. So this is basically the power equations. But I'm not going to ask you anything about Poynting vector, but in case you're reading, coming across this term, hopefully you remember, what to look for. So to the next topic is now what we've been saying is, okay, I have an AC circuit, fine. And any AC circuit will radiate electromagnetic wave. And I know the electric field and H field that radiate, they are related, E and H. And I know one, I know the other, right? And so what's the next thing? Well, how do I use it? To be able to use it, first of all, we need to define the directions. The direction of what? Of what is the orientation of the E field and H field and also the K, right? All three directions. So let's define the direction by looking at the electric field. So we always define we call the polarization by electric field. If the electric field is given by cosine omega t minus beta z, that means it's oscillating along the plus or minus x direction. And also at the same time, it's propagating to the plus z direction. So if this is x, this is y, c is coming out of the board. So what I'm saying is this wave function is oscillating left and right, and at the same time it's traveling out of the page to you, right? That's how the wave look like. So because the electric field is oscillating left and right, we call this a horizontal polarization. This is part of a linear polarization. Linear means it just oscillates in one direction. It does not change. Okay. If I have the second electric field, which is oscillating along the y direction, but also propagating out the z direction, then the electric field is oscillating up and down, and also going out of the page to you, right? It's still a linear polarization in this case because it's oscillating vertically. We call it a vertical polarization. So if I have a linear combination of these two linear polarization, as long as the frequency and wavelength are the same and the phase are the same, it's like adding two vectors. I'm adding a vector along the x with a vector along the y. What do I get? I get a vector somewhat diagonal to the rectangle, right? So that means when I add these two together, the electric field is going to oscillate along this angle, but at the same time is propagating out. It's still a linear polarization. So a linear polarization add on to another linear polarization, as long as the frequency, wavelength, phase are the same, it's still a linear polarization. All right. So the reason we have to separate this because the behavior of the electric field are very different once they hit another surface, another medium. We'll talk about that a little bit later, I hope. Right. And that's why we have polarized sunglasses. It's because of polarization difference. All right. Linear polarization is easy to understand, but what if I still have two of this wave, well, E1 and E2, they are one along the X, one along the Y, so one is horizontal, the other one is vertical, but they are not in phase. One is cosine, one is sine. They're 90-degree out of phase. Then what happened? Then let's look at, again, we said always look at when time goes to zero, right? When time is zero, sine at origin. So when t is zero, z is zero, I have sine zero is zero, right? That means the total electric field at that time is only E1 along the X direction. Are you with me? Hello? Hello? Are you with me? Okay. So as time goes on, what happened? My cosine, the horizontal components begins to swing, get a little smaller. But at the same time, the sine components pick up a little bit along the Y direction. So now I have X direction is a little shorter, I have a little Y direction. So that means the total electric field now is at this angle. As time goes on, the electric field keeps sweeping around a circle like this. At the same time, the electric field is still propagating outward. In other words, as it is propagating outward, the electric field, the direction rotates. It's like, driving a screw. Because we are using the right hand to describe it, we call this a right-hand circular polarization. Why right hand? The thumb is my K. The electric field rotates this way. From time t is 0 to t is 0 plus. Okay, this is how we determine the polarization. Right? You all follow that, right? The thumb is always the K, propagation. I'm using the right hand to describe this. So this is the right hand circular polarization. Below here is just a different fancy way to write the sine and cosine using complex number. I'm going to skip it. Right? If you want to know more, come see me. The picture is this. So if I have a field just oscillating along the X plane and traveling outward, horizontal polarization, linear. If the electric field is oscillating vertically and coming outward, traveling outward, then we call it still linear polarization, but vertical polarization, right? But if these two are not in phase, when I add them together, 90-degree out of phase, what does that mean? That means when this is maximum, the vertical one, is minimum. When the vertical one is maximum, the horizontal one is minimum, right? They're 90-degree out of phase. When you add together, the electric field rotate and is propagating outward, right? The electric field actually rotate. Okay. So this is called circular polarization. Right hand, yes.
In this picture, it's not showing the magnetic.
Not showing the magnetic field. They both are electric field. Okay. So let me go back and make one thing really clear. So if I ask you, how can I make a circular polarization? it takes a few things. One is it has to be a combination of two waves. I call it E1 and E2. I think I just make up the notation. The one is with cosine, the two is with sine. You don't have to follow this notation. You can create your own as long as I know what you mean, right? So it has to be a combination of two waves. One has to be cosine, the other one is sine. They're 90-degree difference in phase. These two waves also are 90-degree difference in space, perpendicular to each other. One is along the x direction, one is along the y direction, right? The third condition is these two amplitudes must be the same. If they are not the same, then you will end up having an ellipse. That means along the x direction have one amplitude, along the y direction have a different amplitude, right? You don't have a circle, you have an ellipse. Okay, let me repeat one more time. In order for you to have a circular polarization, these three conditions must be met. The two waves that you add must be 90-degree in phase difference. One is sine, one is cosine. They must be 90-degree in space, perpendicular to each other. And then these two amplitudes must be the same. If any one of these conditions fail, it is not a circular polarization. Most likely elliptical. Okay, remember this. Yes. 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 Now I'm not gonna. Let me follow this first. So that was the left hand, right hand. But what about left hand? Left hand is, in this case, I have two waves. One is cosine, one is sine, right? And last time I have a plus, this time I have a minus, but don't remember this. Don't say, oh, if I see a negative, that's the left hand. No, that's not what it means. It really depends on what's the direction of propagation and which one is the X, which one is the Y. So don't follow any of the rule, right? How do you figure out it's left hand or right hand? Do exactly what I did earlier. Look at when t is equal to 0, when z is equal to 0, what's the direction of the electric field? As time goes on, which direction the electric field would move to. So in this case, for example, so the electric field at 0, 0 would be, I have no sine term, I only have this term, so everything is along the x direction when t is 0. As time goes on, my horizontal components get smaller, my vertical components along the negative y direction pick up a little bit. So now that means the electric field now moves down, right? But the wave is still propagating in the perceived direction, which is still coming out of the page. So there we go. I try to match it. The thumb is my K, my X is here. Wait a minute, it does not go up this way. I cannot use the right hand to describe this center rotation. I have to use my left hand. Right? So in this case, we call this a left hand circular polarization. Are we okay? So why circular polarization? Well, circular polarization is not just man-made. In nature, we do have circular polarization, right? For example, one type of beetle, this kind of beetles, they reflect, the reflection of the shell is left-hand circular polarization, polarized light. What does that mean? How do they produce that? Well, that has to tie with the molecule structure. When the light come off, like reflect off, they follow the rotation of the molecule, the structure of the molecule. So, depends on the helix, it's left or right, they will rotate one way or the other. So what do animals or insects use circular polarization of? So circular polarization is superior than linear polarization in the sense that you can get a much better signal to noise ratio, even for us, right? So our cell phone is circular polarized. So how does that work? So imagine I'm trying to send a signal to you, but the signal is very weak because it has to travel a long distance, right? Very weak. And so is the noise. So when you look at your signal and the noise, a lot of times you cannot pick out the signal. You don't know if that's a signal or is that a noise, right? But if your signal is rotating, let's say clockwise, and I'm setting antenna to pick up just the clockwise signal, the noise would not have the same clockwise rotation at the same frequency. The chance is very small. So that means you have a much better chance, at least 10 dB, 20 dB better chance. That means 10 times or 100 times better chance to pick out the signal, right? So that's one reason we use circular polarization. It gives you much better signal to noise ratio. You can pick out your signal even at a very weak. Our TV stations coming in or the cell phone, the powers are very low. These are in microwatt or nanowatt, very low power, right? How do we pick it up? One of the technique we use circular. How do I know we use circular polarization? There's another advantage of using circular polarization. So imagine if the cell phone tower is sending a linear signal to me, let's say vertical. That means the electric field oscillating, this one. And I'm holding the phone, the old phone has an antenna, right? Lining up, that's perfect. I line up the electric field, I can pick up a really good signal. I'm tired, I lay down on the back. All of a sudden, my electric field, my antenna is perpendicular to the electric field. I pick up nothing. I don't pick up anything. So that means really, do you hear anything? Depends on how you hold your handset. That's not how we want to use a handset, right? So one way to get around is make sure the signal sent to us is all direction, circular. Then doesn't matter, I'm over here, I'll still pick up the signal. Right? Maybe a little weaker, 3 dB lower, that means half power. But that's okay, 3 dB is not much. I have amplifier. Right?
What if you do a backflip at the same
But
frequency of rotation?
well, unless you flip faster than the microwave signal, which is like 1 billion times in 1 second,
Okay.
then you're not going to screw up your signal.
But theoretically, it's possible.
Theoretical. If you can rotate that fast, then we have to use a different communications technique. This type of swim, mantis swim, and for those who can read Chinese, this is called a piscine swim. You have heard of that? Have you ate that before? It's one of those cool dishes. But anyway, there's a whole talk on this swim. It's not because of the polarization, circular polarization characteristics, but because it can kick with like extreme force because it's so fast, so tiny swim. The force it kick is like extremely awesome. I'm not going to go through much of that. So polarizer. So a lot of the material, they have optical axis. That means the light, when they go through the material, has a preferred direction. Again, that depends on the molecule alignment, the crystal alignment of what made up of this. Our polarizing glasses has a very well-defined polarization direction. That's why we pay a few more dollars for that. For those who watch 3D movie, we have to put on the glasses. What is it? It's just a polarizing glasses, except one of the axis is rotated. So you have one lens with vertical optical axis, the other one is horizontal. So that means one eye can only see one image, the other eye see the other image. They're slightly different on the screen. So when you pick it out, our brain is so clever, it put it together and produce that three-dimensional field, right? That's how 3D movie works. And if you rotate your polarized lenses, like if you have 2 pairs of sunglasses, you can play with this. Overlay them, it get darker. But as you rotate it, now you block everything because the first one blocked all the horizontal light and the other one blocked all the vertical light. So now you have nothing to go through, right? Unless you put something in between, That's amazing. So if I have two polarizer, one is vertical, one is horizontal, but if I can put something to rotate the electric field, then I still have light go through, still have signal go through, right? So let's say the first one is vertical, so all the signal go through has vertical polarizations. But when you go through the second polarizer has a tilde, with a tilde optical axis, then all the electric field will tilt at that angle with a low intensity, of course. Then when it goes to the third analyzer, it tilted again. So the final result is you get a non-zero emission, right? Now we use a lot of this type of techniques in which there's so many applications. I don't know them all, but I only know a few. So some of the calculator use this type of techniques. So if you have a display, let's say the light coming from the back, you have polarizer, and then you have a piezoelectric. That means the dielectric constant can change over if you apply different voltage, right? That means if I apply different voltage, I actually can rotate the light, right? Once I rotate the light will go through. If I stop it, nothing go through. So when I look at the displays, it might be dark, right, black, but I can, electronically turn on the voltage. Now I see a line. So that's how some of the old calculator works. Elliptical polarization, we're not going to do that. Like I say, the three conditions must be correct to have a circular, right? The two waves must be 90 degree in phase, 90 degree in space, perpendicular, and the amplitude must be the same. If one of them fail, most likely you will have elliptical. Now I actually in my book I put a little bit more into it, but we're gonna skip it because in practice nobody really do this. No one would really design elliptical polarization, and nobody really care about the tilde axis. So in reality, we almost have no pure circular polarization because it's so hard to find the two signal would propagate with the same property, vertical and horizontal. So we always have a slightly elliptical, and then to line up the signal, sometimes the technician, you just walk the antenna back a little bit or forward a little bit, so we will shift the phase. So nobody really care about this calculation anymore. So I'm not gonna do that. I'm not gonna test you on that. I'm not gonna talk about it. If you're interested, read it, right? Any questions? No, then we're gonna do an example. Yes.
With that first line, it's filtering out everything that's not vertical, right?
This one
On the left,
on the left.
that's basically filtering out everything that's not vertical.
That's right.
So then when you apply a filter at a different angle, isn't that basically cutting it down? Like it's still going to be a vertical component traveling through, but just smaller.
Yes.
So why do we draw it as a
Tilde.
tilted component?
Because they also pick up the other angle, the horizontal one,
But
that
then
wasn't there before.
we just get rid of all that.
Huh?
Didn't we get rid of all the horizontal parts by using that guy?
Yeah, but the way you can rotate the light is you excite the horizontal part, even when it's not there. Or you tilt it, you rotate it. If you think of like, okay, I have a helix inside, the electric field will match, the tip of the arrow will match the helix. Right? Oh, I forgot to show you this. Until I this way. So I know you don't always read my book, I know. But if you do, I want to show you something cool. Is it chapter 7? Yes, chapter 7. Plain back. So you might think, well, it takes like very fancy material to be able to rotate light or signal in general, but it's not true. Some simple material like this, let me show you this. Yeah, this is fine. I use Scotch tape and put the Scotch tape between the two polarizer and just rotate one of the polarizer at different angle. You can see the Scotch tape overlay and it shows different color because you have different thickness, so different frequency. We go through, rotate a different angle. It's pretty cool. I mean, if you have 4-eye lenses, it's not expensive. You can buy some online, or get 2 4-eye sunglasses. You can play with this. So I put a SU here and rotate the polarizer, one of them, and I get all kind of different color, different shape. You know, cool to play with. That's what I do in my spare time. So sad. Okay, so example. A lot of problem would I would face the problem with this. So at t is equal to 0, I have, let's say I give you a E field. Y hat, 20 volts per meter. K, the direction is 3, 4, 5 triangle, 3x hat minus 4c hat over 5. The dielectric constant of the material is equal to 4. The frequency is 159.2 megahertz. I want to find H. Oh, I want to do one more. And this is a left-hand circular polarized wave signal. Put it in here. Okay, is the question clear? The question is always very simple, right? I mean, the way I stay there, I try to make it easier on myself. Okay. So this is not in vacuum because I give you the dielectric constant of the medium, right? Okay. So we're going to use the 3 rules. So I want to find H, so I'm going to see if I know E first, right? Can I write down what E field is? What is E? Well, what does E00 means? Right? So remember time is 0 and at the origin, the only term you see is the cosine term. And that's the term I call it E1, right? Are you with me? Remember we say circular polarized wave, you have to have 2 terms, E1 and E2, H1 and H2. What does E1 and E2 means? The 1 is the cosine term, the 2 is the sine term, right? When t is equal to 0 at the origin, we only see the E1 or H1. We don't see the E2. We don't see the sine. Sine 0 is 0. So from here, I can write E1, right, for any time t at any position. That is equal to the direction, oscillation direction is y hat, that's given. the amplitude is 20, that is given, right? And then because this is E1, I know this is cosine, that is given, right? And then inside must be cosine omega t minus kx or ky, kc, that kind of thing, right? So what should I write? Omega t. Okay, the first time I'm going to write this first. Okay, omega t. What is omega? Frequencies is 159.2. Why am I so specific on this number? Because if I multiply that with 2 pi, I get 2 pi is around 6. So 6 times this is about 1,000. So 2 pi f, which is omega, is roughly about 1,000 times mega. Mega is 10 to the what? 6. So that means omega is 10 to the 9. Right? I always use 159.2 or 1,509.2 just so that you can write omega without using a calculator. I'm sure a lot of you still punch in the calculator in the exam. But the idea was try to make it easier for you or for myself when I'm doing example. So that's omega. I'm going to put that in later. And then what do I write next? Omega t minus k dot, right, in 3 dimensions, k dot. What should I write here? That goes to here, right? What is k hat? If I write it, this is 0.6 x hat minus 0.8 y hat, c hat, sorry. Right? And remember what we say about reading off the k of this type of formula? Let's say this is 30x plus 40y. What is the k? Negative of this and put a hat on. So this is positive 30x hat, negative 40y hat, right? Okay, so if I know k, I know what to write here. Correct? Okay, but do we know k? Well, this is k hat. Is that k? It's not k. What do I need to make it a k? I need the magnitude, right? This is only the direction. How do I find the magnitude of k? Well, we did that before the exam. I'm sure you gave it back to me already. So let's do that again. We look at the velocity. So the velocity is omega over k, right? We know omega. What is velocity? Velocity is z over n. What is n? Index of reflection. What is index of reflection? Square root of the dielectric constant. Right? This is very useful. So now I can write, I want to find k, right? So I relate this to, I can tell you k is equal to omega times the square root of the dielectric constant, which is n divided by c. Omega is 10 to the 9. We just calculated. Epsilon, dielectric constant is 4, so square root of 4 is 2. Divided by speed of light is 3 times 10 to the 8. So this is 2 over 20 over 3. Right? Are we okay? So what is my k vector then? My k vector would be the magnitude is 20 over 3. The direction is 3x hat minus 4c hat over 5. That becomes 4. So this is 12x hat minus 16. I'll just write it 4 outside when I do it. I don't need to make it so complicated. is equal to 4/3 3x hat minus 4c hat. Right? That's my k. Right? All right. So now I know k. What do I write in my expression? What do I write here? You just negative of this and remove all the hat. So this is negative 4/3 times 3x minus 4c. Make sure you do not write a hat here because it's wrong. You cannot have any vector inside the sine and cosine. You cannot have any vector in the denominator. And then the unit is volt per meter. Any question? Up to this point. The new material here that I'm gonna ask you in the exam, all this material is new to you, I understand. But they don't require the calculus that we require for the first two midterm. There's no definite integral, there's no calculus, which a lot of you really don't like, I understand. Right? So in a way, these are easier, but they are new. So if you learn it well, you should do well. Questions? W over what? Oh, this one? V, sorry, velocity. I know it looks like a W. Velocity is omega over k, is C over n. N is square root of dielectric constant. Are we okay? So far, so good? All right. So once we know this, if I know E1, I should be able to find E2, right? Because E1, E2 will give me the propagation, left hand, right hand. But do I need to find E2? Not really, because I want to find H. So I can just go from E1 to H1, and then from H1 to find H2. Right? You can go any way you want, but since I'm not asked what E2 is, I'm not going to go there. You have a question? Why is V C over V? And why is C is a velocity? What? C over N. Remember in physics 52, the index of refraction is defined as a ratio of the velocity of light in vacuum versus in a material. That is defined as the index of refraction. That tells you how much light band if your light get into that medium. So V is C over N. It's okay. Okay now?
No, that's not twice. Not vector.
Why is the velocity? Because we're talking about the magnitude of the velocity, right? I mean, if you want to put it as a vector, it's okay, but it's not going to change anything. So let me start from here and find H1, right? How do I find H1? I'm going to use the three rules, for example. Okay. So E1 is this, I'm going to start writing H1. So the first rule is E and H are in phase. So H1 is, I don't know what's the direction, I don't know what's the magnitude, but I know this is going to be cosine omega is 10 to the 9 t minus, I'm gonna remove everything. Oh, the 3 cancel. For x minus 16 over 3 plus z, right? I'm just gonna copy the whole thing down here, except I substitute the value, right? Right? So, and the unit, what's the unit? For electric field is volt per meter, for H magnetic field is M per meter, right? Just write this down, at least you get a few points. Oh, I'm happy nobody gets 0 this time. So I have more people get 100% than 0, which is good. Right? Okay, so now how do I find the direction? Rule number 1 is this. Rule number 2 is E equals H is K. So what is K? Let me look at this here. K is 3x hat minus 4c hat, the ratio. So I'm going to draw, let's say, x and z. Right? Where is my y? Positive y, in or out? Okay, so 3x, 3 unit on the x, minus 4. So this is my k, right? 3-4 ratio. And my E field is along E1. It's along the y direction, right? And we say y is into the page. So that means, let me draw this. That means my E1 is into the page. Now E cross H is K, so where is my H? E is my fingers going into the page. K is my thumb. So where's my palm facing? In the first quadrant, right? This is my H1. Right? Okay, so how do I describe this direction? Well, K is 3-4 ratio, X to Z. Then H must be 4-3 ratio. So that means the direction of H1 must be 4 on the X, positive, and 3 on the Z, also positive. And then if I normalize it, that would be 3, 4, 5 again. Right? So this is what I'm going to write in my direction. 4x hat plus 3c hat. Right? Direction, the amplitude, the wave, the unit. What's left? The amplitude. How do I find the amplitude? Well, E naught over H naught is eta. Right? So let's do that. So I'm going to write E naught over H naught is eta. That means H naught is E naught over eta. But what is eta? Eta, it's complicated. Square root mu over epsilon. But, oh, not to worry. We say eta is eta naught divided by n. Right? Eta is square root of mu over epsilon. I say try to use eta naught as much as possible. So what does that mean? What is eta naught? 377 ohms. What is n? square root of the dielectric constant. So this is 377 over 2, right? So put it in here. So what is H naught? H naught is E naught. What is E naught? 20, I think. 20, right? The amplitude of E field is 20, right? So E naught is 20. And then divided by 377 and then multiply by 2. So 40 over 377. I'm just going to put it in here. Any question? So what is 40 over 377? Let me do one more step. (0.106), right? So a lot of times, let's look at this expression. The magnetic field, magnitude, is the electric field divided by 377. 377 usually is much bigger than the amplitude of the electric field, right? So this number usually is a couple order of magnitude smaller than the electric field. So very often we use milliamp. So let me write it. So this is 106. So let me write it down first. So this is equal to 0.106, right? Amp per meter. But a lot of times I write it as milliamp per meter. It's very common we use, like when was the last time you used amp in your circuit? Hardly, right? Always milliamp, right? But I just want to point this out and warn you, the amp, these two amp are not the same amp, so don't cancel it. Don't say, oh, these are just A. They're not, right? It's milliamp per meter. So I'm just going to write 106 over here. And change it to milliamp. Again, in your final, if you're writing the exam, simplify this. Don't make me, I keep saying that students still make me do the math. Multiply it out, give me a simple number, something x hat plus something z hat. Don't make me have to do the multiplication to check your answer, right? If you make me do work, you're going to pay, right? Okay. But for my example, I'm just going to leave it like. So now what's left? I know H1, I have to find H2. What is H2? Well, because I have to have H1, H2, or E1, E2 to make a circular polarization. I only find one. I need to have two terms. So how do I find H2? So one easy way to think of this is, remember how do we determine whether it's right hand or left hand? Is like if thumb is my K, I want to know, E1 go into E2, do I use the right hand or left hand? So I'm like doing a cross product. E1 cross E2 is K, except I need to know whether I'm using right hand or left hand. Are you following me? So E1 and E2, they're perpendicular, right? One of the conditions of the circular polarization is these two waves must be 90 degrees in space. That means they're perpendicular. One is X hat, one is Y hat, right? So that means E1 cross E2 will give me K, either left hand or right hand. Are you following me? Let me write it down. What I'm saying is E1 cross E2 or H1 cross H2, the same thing, will give me, these are all hat direction only. If I use right hand, then this is a right hand circular polarization. If I use left hand to do this cross product, then it's a left hand circular polarization. Right? So as H1 cross H2, same thing. Doesn't matter because E and H, they always go together. Right? Oh, what does that mean to us in this example? I know what H1 is now. Can I find H2? Yeah. I'm just going to write it down. So H1 is this. H2. I know I have a direction. I'll figure this out. I know I have an amplitude, but the amplitude must be 106. How do I know that? Because it's circular polarization, right? If they're different, then we would not have a circular polarization. And then what was the phase? Well, this is cosine, then mine must be sine, right? 90. And the rest must be the same. 10 to the 90 minus 4x plus 16 over 3 z medium over meter. See, all of a sudden, all we left is the direction, right? It's not difficult. You just have to do it a couple times. So again, please go back and redo this example. I've been saying that throughout the whole semester already. So how do I figure out the direction? Is this a left hand or right hand? This is, we say it's a left hand circular polarization, right? So let me go back here. What does that mean? If this is my H1, this is my K, I'm going to use my left hand because it's left hand circular polarization. The fingers is my H1, the thumb is my K. Where's my palm facing at? Into the page. So my E2, my H2 direction is into the page. Into the page is Y, plus Y. So the direction is just Y hat. Then you're done. You have H1, H2. I know your total H field is H1 plus H2. You don't even have to write it. Right? If you follow my notation, I know what you're talking about.
Can you go through that y hat again?
Huh?
Can you go through that y hat again?
All right, go through Y hat again. Right? So I know H1, what H1 is, the direction. I know this is a left-hand circular polarization. So that means H1 cross H2 using my left hand will give me K. So the first vector, H1 is my fingers, K is my thumb. So where's my palm facing? Into the page. That means H2 is into the page. But into the page is positive Y hat. So that means the direction of H2 is Y hat. If this is a right-hand circular polarization, we do the same thing with my right hand. Fingers is my H1, the K is my thumb. So now my palm is facing outward, that means my H2 would be out. But in is plus Y hat, then out must be minus Y hat. So my H2 direction would be minus Y hat. Are you with me? E1, E2 is K, or H1, H2 is K, right hand, left hand. E cross H is K is always right hand, regardless what polarization. E cross H is always using the right hand. Right, that's the Maxwell equation. Only E1, E2 to K, or H1, H2 to K, then depends on the polarization sense. Right hand or left hand. Right? Everything else, right hand. Questions?
So the polarization be given to me, oh, it's right.
So yes, so most of the time will be given to you, but I could also give you a problem. I give you the whole expressions, like one of your homework. So for example, let's do this really quick for 1 minute. Let's say I give you an electric field, which is x 2 cosine omega t plus 300 z minus y hat 3 sine omega t plus 300z. For example, I asked you what's the polarization here. Okay. So looking at this, number one, the two amplitudes are different, so it cannot be circular. It must be elliptical, right? And then as far as the right hand, left hand, then we do the same thing. We say at t is equal to 0 and z is equal to 0, I only see the cosine term. The cosine term is along the x, so this is t is 0, right? T is 0. As time goes on, this gets smaller, but I'm getting a minus y, so that means the electric field point this way, rotate this way, right? This is x and y, right? X here, y here, where is the positive z? Coming out, right? The propagation direction is what? Negative z. K is into the page. So now we use the thumb pointing into the page. The finger is here. I use the right hand. I don't use the left hand. So this is the right hand elliptical polarization. RHEP. Right? Any questions? Practice the field, they are not really difficult, right? You should be able to nail this, at least one problem in the exam now. Any questions? All right, we'll move on to a new topic. Next test.
What topic?
Lossy media. Now we go into a real material.